So now it is okay, right?
Yes, sir. Yes, sir.
Okay, so broadly, okay, so types of algorithm can be broadly classified as supervised learning and unsupervised learning. Okay, so this supervised learning and unsupervised learning further classifies as classification, regression, machine learning, deep learning. So we need to understand how this classification happens. Okay, how this has been divided. So we have the data. Okay, data as a discrete data type and continuous data type. Okay, if we have a discrete data type and we apply some algorithm on it, then that algorithm name is classification or categorization. Okay, so this comes under supervised learning. If we apply a machine learning algorithm for discrete data, okay, with unsupervised learning, then it comes under the clustering. Continuous data, okay, will be like regression. Okay, so if I say in words, we cannot understand. So I will show the example. Okay, so this is the data type. Okay, so the data type we are going to work for our example of defect detection is the grading data set where this target variable is either yes or no. So it comes under the category. It comes under the category or discrete. Okay, it's going to be like either it's going to be comes under yes or it's going to comes under no. So this is the data for this example of classification. Okay, which comes under the supervised learning. Done. If we see for example for clustering, regression. Okay, we'll be having a value x1 and x2. Our target is going to be like y. So it's going to have the continuous values. The continuous values, okay, if we apply that algorithm, it comes under the regression. If we have the value, okay, if we have the value, something like this, okay, cylinder, okay, some cylinder, then what is the HP, then what is the capacity of this, and what is the gear, then what is the mileage per gallon, okay, but our target value here is missing. Okay, our target value is missing. If we want to do some kind of research on this, this will come under the clustering. Okay, so we have three data set. Okay, data set one is, okay, we'll be having a class either yes or no. Okay, or we can say as cancerous or non-cancerous, cancerous or non-cancerous, defect or non-defect. Okay, like that. Then regression will have, okay, so this is like one. Then this regression algorithm where we will have a continuous data that starts from range of some 1 to 100. Whichever is giving under this 1 to 100, okay, it will give the regression analysis. Then third one is we will be not having the values of what is the target, but we need to categorize it. We need to categorize it. It comes under the clustering. Then fourth one is a dimensional reduction. Okay, we are not going to see anything on that, so I am skipping them. So now let me clearly explain what is the supervised learning. Okay, so supervised learning, okay, now we know supervised learning can be applied for two kind of data set. One is going to be like continuous data set or it can be a discrete data set. Okay, anything. Okay, so if it is continuous, okay, if it is continuous, then it's going to be like classification. Okay, sorry, it's going to be like regression. If it is discrete, it's going to be like classification. Okay, whatever it may be. So my input, okay, input is going to be like X, then output is going to be like Y. Okay, so this is what the table. Okay, this input, okay, this X can be like X1, X2, X3, anything. These are all the attributes. These are all the attributes. Based on this attributes, I will be getting this Y. I will be getting this Y. So we are going to map the relationship between this X and Y. Okay, this Y is depends on this X. Okay, X is an independent variable. Y is a dependent variable on the X. As X changes, Y may change. Okay, as X changes, Y will change. Okay, that is what our model is. So we need to find the relationship of this model. Then we are going to have the relationship. Okay, Y equal to F of X. Y equal to F of X. Okay, if I am going to give, okay, if my X is going to be like 1. Okay, if X is going to be like 1, my Y may be like 2. Okay, if it's going to be like 2, then it's going to be like 4. Okay, it's going to be like 3, then it's going to be like 6. So which means my Y, okay, will be like, okay, so if that function, okay, function of X is going to be like 2X. Okay, 2X, that can have some constant values applied to it. So it depends on this impurity. Okay, so impurity we can add. Okay, we can add or we can subtract. So this is what the supervised learning algorithm. Then the supervised learning algorithm will have two phases. One is training, testing, then prediction. Okay. So what are all the data set that we have? We will split as 70 and 30. We will split as 70 and 30. We will train the model. Then we will create the model. Okay. Then we will test the existing remaining 30% of our data for the validation. If the 30% is correct, then we will go for prediction. Okay. We'll supply a new value. Then for that value, we will get the output. So this is what the supervised learning is. Okay. So the next part is counterpart is unsupervised learning. So same data will be there. For that, we will be having a vectors, but only thing is we will not have the class label. So we will not have a y. Okay, so there we have x to y. Here we will not have this y. We need to find this y. So it comes under the clustering. So if we see, okay, both the approach in a single slide, then we can easily understand. So this is like classification, then this is the clustering. This is the one which is available on the right side is there is a supervised learning. On the left side is unsupervised learning. Only difference is we will not have this class label in this unsupervised learning. So example for understanding what is unsupervised learning. So this is my data set. So this is my data set. If I'm going to apply some algorithm on it, it is going to categorize this into either birds or animals. If it is like animal means, okay, it's like dangerous animal or not. So it may divide like based on the property. So it has 2 legs, it has 2 legs. Okay, then it has 4 legs and 2 legs. Okay, based on this, it's going to categorize as 2 leg and 4 leg. Then again in this both will have a 4 legs. Okay, but the property of air is hair is differ here. So it will divide into further 2. Okay, so this is what the unsupervised learning example. Okay, now we will come for our part of defect detection. Okay, till now I have given an introduction about what is learning algorithm. Okay, learning algorithm can be 2 types. One is supervised or unsupervised based on the data set. Okay, based on the data set. Okay, normally if it is a defect detection, we will work under a classification part only. We will not work for the clustering. Okay, for example here. Okay, so this figure 1 indicates this one type of defect detection where we can observe the heat emitted by the body. Okay, we can have a sensor for evaluating the constant temperature here. If the temperature around the surface is constant, then we can say that particular material is not defected. Okay, if it has some defect somewhere here, the reflectivity property of that particular defect part will be either high or either low. Based on this difference, we can detect, then it's going to be like it's having the defect. Okay, this will comes under the image processing and sensors. Then again, the next one using a machine learning, okay, and a computer vision. So first data set, okay, the first data set is the original data set. Original data set, it has the tablets. Okay, it has the tablets, okay, in the rows and columns. Okay, in the rows and columns, it has a tablet. Then the next one is a tablet with some defect, with some white spot on it. Okay, so we can extract the features from it. We can extract the feature from it. Then we can extract the feature from it. Then we can match both the features. Then we can say there is some difference here. So, and we can know, okay, we can know, okay, what is this? Okay, as it's going to be like the classification, it will have a class label. Okay, so it will say it's going to be like the tablet has some defect on it. Okay, then there may be a chance some tablet is missing, some tablet is broken. Okay, based on the image processing steps, we can identify this. Okay, so this is the 2 kind of defect detection. Okay, that are frequently used by many researchers. Okay, so here this thermal camera has been used for the defect detection in material science. Okay, whereas this can be used in n number of applications, like even additive manufacturing. Okay, where while welding, okay, there will be, okay, for layer by layer. Okay, so they will be scanning. Then they will be identifying any foreign materials is available or not, foreign parts. Then we'll spend some time on what are all the defects that is available in the materials. Okay, that is imperfection. okay, in a material quality, that is shape, size, or structure. Okay, or we can have a point defect, surface defect, or volumetric defect, that is in a strength or any scratches or something. Okay, then surface defect. Okay, it's like boundaries. Okay, not in the correct shape or whatever. Okay, different texture. Okay, that comes under the surface defect. So these are all few input images that is available for this materials where it's a strain. Okay, some dust is available in the particle, some hairline, it may be a crack or it may be like a scratch or whatever it is. Okay, or in a glass we can have a scratches. Okay, this and all can be identified. Okay, by the computer algorithm. Done. If defect detection can be applied in various domains like automotive, electronic parts, buildings, okay, then even raw materials, foods, medical, and others. Okay, so here, whatever may be, okay, the type of defects can be scratches, cracks, dirt, or dent. Okay, it depends on whatever it is. Okay, so there may be like a loose contact in electrical parts, or building material, in building material cracks, and everything. These are all can be identified by the image processing techniques. Then these are all a few sample inputs. Okay, where we have an image. Okay, here it's a defect image. Okay, then as a defect here. So here this bolt, okay, it has a defect at this part. So closer image says this. Okay, then here is the brush. Okay, we have the bristles that's coming outside. Okay, the electrical component where our connection has been gone off. Okay, so this is the zip that we are using in shirts, pants, where we have the defects there. Okay, so as okay, we are seeing this in a naked eye, or we are easily identifying this. As this manufacturing unit will do, okay, like in tons, okay, in a day. Okay, they cannot check that manually. So they need an automated process where, okay, this nails will go on conveyor where our vision image processing techniques, okay, will scan this image, then it will check for the proper structure. If it is a proper structure, then it will push on the different conveyor. If it is on a improper structure, then it will push on to the different conveyor. Okay, so this is another example of okay, so for defects. Okay, so good, okay, it's the color or hole or scratches. So this is all the different defects that is available. Okay, so this is available okay in the internet also. Now we'll come into the part of how to identify that. Okay, so we'll be giving an input as an image. From the image we will be extracting the features. Okay, then image 1 will have the features. Okay, then image will have a feature 1, will have a feature 2, will have a feature 3. Image 2 will have a feature 1, then we'll have a feature 2, then it will have a feature 3. Like that, if we have 800 to 9,000 of image, for everything, it will extract these features. This feature 1 is a value that is associated with the algorithm. Okay, then based on these features, okay, the relationship between a feature 1, feature 2, and feature 3, it will be classified as class 1. It may be classified as class 2. It may be, okay, the remaining thing can be classified as class 1. If the same set of relationship is available in a new data set, then it will classify as class 1. Okay, so based on these features, okay, if a new input is coming, okay, it will classify that as a either a cluster, there is a classification 1 or classification 2. Okay, so that approaches. Okay, here we are extracting these features. No, this feature approaches can be this texture based or color based or shape based. Okay, this texture based means GLCM or morphological operation. All this approach will detect only an external defect. Okay, if we want to identify the internal defect, then we need to go for thermal scanning only. Okay, so all this approach, whatever that I'm showing here, will detect only the external approach, external defect. Okay, so here if it is a GLCM, it's going to be like for a ceramic material. Okay, then its recognition rate has been given as 92.31 by existing authors. Okay, then color based. Okay, color based. Okay, bivariant color histogram. Okay, it's a particle board. Okay, so it can effectively detect and localize the defect that is available. Okay, so I have given the reference at the end for all these things. These are all the approaches. Okay, now this is the real-time data that we have worked on this. Okay, then this is the defect detection in a leather. All the inputs, all the samples. Okay, this is the leather products. Okay, each and every sample are leather products. So this is the growth mark. Okay, the growth mark here. Okay, the growth mark is a folding mark and is the grain of as a loose grains, pinholes, and it's a non-defective. Okay, so on applying an image processing technique, okay, using a feature extraction, okay, here we have applied a convolutional neural network for getting this input, getting this values. Okay, based on this, for understanding purpose, I have converted that to the data set. Actually, this data set will not exist in a real application. Okay, real application. I have categorized this folding marks. That is folding marks as the rank. Okay, if it is high rank means then it has the quality is good. Okay, if it is lesser than 8, the quality is not good. Okay, grains of. Okay, grains of means we have given the value as either yes or no. Okay, similarly, growth mark. Okay, based on the value what we obtained here, based on the value what we obtained for each and every folding marks, we will be having a values. Okay, for classification purpose, then for this theoretical study purpose. Okay, the theoretical study purpose, I have converted the values into this table. Actually, in real time, if you open the values, it will not be like this. It will not be like this. Okay, it will have the values. Okay, so now this is the table. Okay, it's going to be our input table. Okay, now this is our inputs. Okay, this is feature 1, this is feature 2, this is feature 3, then this is feature 4. Then this is our target. Okay, yes indicate it is not defective. No indicate it is going to be like defective. Okay, here this folding rank indicates it's the higher rank, its quality is high. Okay, so this is our first instance. If greater than, okay, if a folding rank is greater than or equal to 9, then grains of is yes, then growth mark is very good, then loose grain is good, then it is not a defective product. It is a good product. Okay, it's a good product. Okay, so based on this value, we are going to perform. Okay, so this is going to be like x1, x2, x3 is the y. Okay, so we need to find the model. Okay, for that, I'm going to use the decision tree. Okay, so this decision, we can use the decision tree, or we can use SVM, or we can use any other, or we can use even CNN also. We can use in deep learning, we can use CNN. Okay, so why decision tree means is the basic algorithm. Okay, that will be easy for understanding. Based on that, we can move to SVM and we can move to CNN as the complexity increases. Okay, so decision tree. Okay, decision tree can be done in different methods. Okay, so one method is going to be like ID3, C4.5, or CART. Okay, so this decision tree will come under the classification part. So which means our data set is going to be like continuous. It's going to be like discrete values. Okay, if any question is there, okay, whether decision tree can be accessible for continuous value. Yes, it is possible. For regression also, we can go for decision tree, that is classification and regression tree. If our target attribute is continuous value, but we need to apply a decision tree, for that we will go for a CART. C4.5 is a recent algorithm, okay, that most of the decision trees, okay, in Google they are using. This ID3, iterative, okay, diagnosis, okay, we are using for a study purpose. So slight modification of ID3 will go for a C4.5. Okay, I will at the end I will say what is that modification. So steps in this decision tree. Okay, so this is what. Okay, so again I'm repeating. Okay, so for the defect detection of this leather, okay, using a computer application, we have transferred that entire data, the entire values of the leathers into the values. Okay, now we are applying this value for creating a model. For creating a model, we are using this value. Okay. So steps. Your first step is to calculate the entropy of a data set. Okay, then we need to understand now what is this entropy. Okay, this entropy is an uncertainty, or it's like what is that? We can say like it's like a surprise that has been there. Okay, if there is a sunny day today, okay, for sunny day, okay, what is the chance of getting rain? Okay, it's very less. Okay, which means if we get rain means it's surprise, right? Like that. Okay, this entropy is a surprise or the uncertainty in the values, or we can say it's like a impurity of the data set that is available. If a entropy is high, okay, then chance of getting is very low. Okay, so for calculating this entropy, we have a formula. Okay, this formula has been already defined. Okay, we are not going to spend any time on deriving this formula. We are already, this is the proven formula. Okay, then what is this P and what is this N? Okay, this P is a positive classification, N is a negative classification. Okay, N is a negative classification. Again, I am saying, okay, if I'm going to go for okay, my blood, okay. I'm going to toss two coins. Okay, in that first it has tail, the next it has tail, only two tails. Okay, entropy of this is going to be like 0. Okay, entropy is going to be there 0 because head has not occurred. Head has not occurred. Okay, so this T, okay, this positive is 1 and negative. Okay, both are positive here. Okay, so we'll go with the next one. Okay, so for each and every attribute, okay, calculate an average information entropy. What is that average information entropy means? Attribute of there is a entropy of each and every attribute that is available. Okay, each and every attribute, then sum it up all the things. Then that is going to be like average information entropy. Then we need to find the average information entropy for finding the gain. Okay, this gain is the difference between your entropy and average information entropy. Okay, so then step number 3 is pick the attribute with the highest gain, then that is going to be a split value. Okay, so why? Okay, now we can, okay, we'll go for this again for this table. So we are going to follow the decision tree. So we need to have something like this. Okay, then it is going to have the value here. Then it is going to have some other values. At the end is going to be like either yes, no, that is yes or no. Okay, so this is what the decision tree. Now we are executing that particular ID3 algorithm for finding which node is going to be a root here. Okay, for finding this root node, we need to execute this many steps. Okay, this many steps. Okay, if you have any doubt in between, okay, or if my voice is not audible, you can raise your hand or you can interrupt me and I'm ready to give an answer for that. Okay, so this is the data set that we have. Again, I am saying this is the real-time data set we have achieved from the computer vision part. Okay. Then in the data set, we have found 4 attributes. One is folding rank. Then grain off, okay, which has 2 values. Then growth mass has 3 values. Loss grains that has 3 values. Okay. Then target attribute. Okay, target attribute condition is good or bad. That has either yes or no. Okay. From this, if you count this 1, 2, 3, 4, 5, 6, 7. So my positive response is 7. Then my negative response is 3. Okay, so we can compute that from the data set, we have 7 positive and 3 negative. So this is what the P and N that we required for our entropy calculation. Okay, then now, what is our first step? First step is to calculate the entropy of an entire table. Okay, so entropy of 7,3. So substitute the values, okay, in the formula, then we will be obtaining this particular value. Okay, or this can be done or like this also. Okay, anyway, this method also, let me say here. Probability. Okay. What is the probability of this particular value? Either yes or no. Okay. Then here it's going to be like entropy. Probability is like 7 by 10. So here 3 by 10. Okay. This entropy is the inverse of 1 by this 7 by 10. Okay, it's 0.7. Okay, that is, if I am going to find the entropy, it's going to be like log base 2. So this is what is mentioned here. Okay, this is what mentioned here. Okay, that is log base 2 of 7 by 7 plus 3. Okay, so this is what mentioned here. So at the end, okay, we can multiply this. So like this also we can calculate. Okay, it's another method available using a probability. Done. This is the overall entropy. Okay, the overall entropy that we found for our particular target attribute. Done. Now, step number 2 is to calculate an average information entropy for folding rank, grain of practical growth. For growth mass, then loose gains. Okay, then we need to execute the step number 2 for 4 times. 4 times for finding this folding rank for each and every 4. If it has 4 attributes, it has to execute for 4 times. Okay, let me unloop this 2.1. Okay, so in 2.1, it's an average information entropy. We need to find an average information entropy. Formula for average information entropy for each and every attribute. Okay, so we cannot easily understand what it is. Okay, let me unloop that formula here. So this positive of this growth particular attribute, then negative of that particular attribute, then entropy of this FR greater than 9. Okay, similarly entropy for greater than 8, similarly entropy for less than 8. Okay, so this is what and unlooping of this particular function, formula. If I want to fill this value, okay, if I want to fill this values, we need to take from the table. Okay, this is the table. Okay, for this FR is a folding rank. Okay, that has 3 category. Greater than or equal to 9 is 1. Then greater than or 8 is 2. Then less than 8 is 3. Greater than or equal to 9, it has 4. From that, 3 yes was there. Then 1 no was there. Okay, similarly here, greater than or equal to 8, all are yes. 4 yes, 0 no's. Here all are no. So that is what we are making as a table here. From this table, we can compute this particular formula. Okay, this 3. Okay, on the whole. Okay, on the 10. Okay, on the 10, I am having 4 values here. From that 4, 3 is positive. Okay, then 1 is negative. Okay, on the remaining 4, okay, 4 is positive, 0 is negative. Okay, on the remaining 2, sorry, here a small mistake, it's going to be like 2. From the remaining 2, okay, we have 0 positive and 2 negatives. Okay, after solving this, we will get this value. Okay, so this is average information entropy. Average information entropy, after finding, we need to find the gain. Okay, gain is going to be like your overall entropy, okay, with this folding rank. Okay, so it's going to be like 0.5564. Okay, 0.5564 is our average information entropy of this particular table. Then we need to find for the next attribute. Okay, similarly, average information entropy of the gain of. So it has 2 attributes. One is yes and one is no. Okay, then we can go for our matrix values. Then we can substitute. Okay, then we are going to get the value of an average information entropy of a second attribute. Okay, this is 2.2. I am skipping 2.3 and 2.4 and I am going for the direct step number 3. By 2.1, I got this values. By 2.2, I get this values. 2.3, then 2.4 that I skipped, I got this value. This is the gain. Okay, now what is my first? Whichever is having a high gain, then that node is going to be my root node. Then that gain is going to be a root node. Okay, then it has three values, greater than or equal to 8, less than or equal to 9, then less than 8. Okay, so here, if it is like greater than 8, for sure its condition is going to be like good. Okay, if it is less than 8, its condition is bad. If it is greater than 9, it has the instance where it has both yes and no. Now we need to repeat our algorithm for the subset. Okay, again, if we repeat the subset for our algorithm, our final decision tree will be something like this. Okay, now this is our model that we built manually from our data set. This is the model. Okay, we told, right? Okay, so yeah, we will be okay. Initially, I told a learning algorithm will have an X, will have the inputs, then it will have a target. It will have a target. Based on the relationship between X and Y, we need to find the model. Here, the model of this particular table is this particular decision tree. Okay, if anything, if you are somewhere it is coming like your FR, okay, it's like your FR is 7. Okay, it will clearly say it is defective. Okay, if FR is greater than 8, okay, it's greater than 8. Okay, then it will not check about anything. Okay, so it's going to be like, okay, if FR is greater than 8, then your grain, okay, its value is condition is good. Okay, then it comes under the category of yes. So this is our model. Okay, this is the model. Okay, now what we are supposed to do means we need to write the Python code for finding this average information. Sorry, let me go for okay here. So step 1, write the Python code for finding the entropy. Okay, this is step 1. Then step 2, write the Python code for finding the average information entropy and find the gain. Okay, then for each and every attribute, it will find the gain. Okay, from that, write the code for sorting it, whichever is on the top, make that as a root node. Make that as a root node. Then for remaining value, call the function again random, that is recursively, then it will draw the tree. It will draw the tree. So this is what the mathematical concept behind your decision tree. Okay, so this particular model can be built with this CNN also. Okay, with the CNN. Okay, this is a CNN. Okay, where okay it will have an input. Okay, where it will have an input. Okay, it will have a layers. It will have a layers. Then for the particular layer, okay, it will extract the features and everything. Okay, I've shown already. I've shown an image, right? That features it will extract. Then it will classify your result as either a defective or non-defective. Okay, so for this, okay, for if you are going to do research on this, we are having this many target that is a data repository available. Okay, so for various material, okay, MV Tech we have, CAHL we have lot of data sets. Okay, then it has for a steel or for metal or for a fabric or for concrete. Okay, or you can go for your own data set also. So these are all the related work, okay, that has been happening in VIT. Okay, in VIT. Okay, so this, okay, if you go through this ORG, okay, it will have this. We have our own data set. Okay, we have our own data set where you can utilize this. Okay, for a while, okay, I can share the. Let me show the Kaggle data set. What is there? Okay. Uh, Okay, is my screen is visible? Sir, is my screen is visible, sir?
Yes, sir. Visible, sir.
Okay. So whatever the data that I've shown, okay, has been from here. So here, folding marks. Okay, it has 600 data. It has 600 data for each and everything. Okay, so from this only I have taken the 10 samples, then I have converted that value. That value conversion is like normalizing. Okay, from that value, okay, if you do, it will go for a wrong answer only, because for understanding the mathematics behind the classification algorithm, I have gone for this. Okay, for each and everything, we will be having a features. Okay, there may be n number of features for a single attribute. This data set is available in a Kaggle for free. Okay, so this has been done in the machine learning lab that is available in a mechanical department in VIT. Okay, so this owned by Professor Dennis Ashok. He's a professor in mechanical department. I am assisting him in developing a learning algorithm. Okay, all this domain knowledge will be supplied by mechanical professors. We will be writing a code, we will be analyzing the code, and we will be finalizing the classification model. So this is what the data set available. You can work on it. So here we have the working code also is available. Whatever that the code that we had, okay, the CNN model that I've shown here, the CNN model that I have shown here, for this, we have the code. Okay, this freely available code is available. You can extract that code and you can start working on it. Okay, so if you have any doubt on this, then you can mail. Okay, you can mail to the professor who is conducting it. Okay, from I will give the code to him. Okay, it's freely available. Okay, in a Kaggle data set, if you are writing a leather defect detection and classification, it's freely available. We have our contact information here also. Through mail you can contact. Okay, so this is the work. Okay, then I am ending my presentation here. If you have any doubt on this, you can ask me. Okay, then I have utilized this time for creating an interest in this particular defect detection with respect to a machine learning approach. So for that I have taken one simple algorithm and I have explained mathematically. Why I have explained mathematically means, if we know how mathematically it works, then only we can fine tune an algorithm. Okay, so instead of this entropy, we can have a Gini index. If I apply Gini index on this particular ID3 algorithm, it's going to work as C4.5. Okay, why not entropy? Okay, instead of entropy, I am going to go use a similarity measure. Okay, I'm going to use some other similarity measure. Okay, so then it's going to be like your own approach. Okay, instead of entropy, you have used what is that similarity measure? Then that is like modified decision tree. Okay, you are a hybrid decision tree, a modified decision tree. Okay, so instead of this entropy, I am going to use some other methods. Okay, that is I have shown here. Okay, so instead of this inside the decision tree, instead of that entropy, I'm going to use some rule-based method there. Okay, then rule-based method. Okay, then it comes under the different category. That is the rule-based algorithm. Okay, rule-based algorithm will have the for a set of rules that can be utilized there. Okay, then we can write the model for this. Okay, all our that is analytical learning algorithm will come under here. First order resolution or anything, anything you can use here. Or we can use the Bayesian learning algorithm. If you use the Bayesian learning algorithm, it's a hybridization of Navy-based and decision tree algorithm. Okay, that is, if we want to apply changes in an existing algorithm, then we need to mathematically understand this algorithm. Okay, so for that only I have gone through mathematical. Okay, so because if I have taken any defect data set, okay, something like this. Okay, so technically, okay, you people are mechanical engineer, you know what is this. Okay, if I take a materials additive manufacturing, okay, if I say some concept on this, then as a mechanical professor, you know better than me. I am a computer science professor. Okay, so I have dealt with respect to maths and with respect to the logical part behind the algorithm. Okay, in the next session, okay, Aarthy ma'am will give libraries related to this concept. Okay, so that is what we planned. Okay, Professor Aarthy will be doing on that is applying this thing on the working environment. Okay, maybe Colab or Orange tool or Jupyter tool. Okay, based on ma'am's convenience. If you have any doubt, you can ask me.
Dear participants, if you have any queries, you can unmute yourself and you can ask your doubts.
Okay. If you don't have doubt, then let me take 2 minutes of extra time for saying where this defect detection is currently happening in a real time. Okay. So everyone knows Wipro, right? Wipro 3D. Wipro 3D. Okay, it's a place where they are manufacturing the aircraft products. Aircraft. Okay, so as an aircraft means it's going to be like the requirement for that is it should be like less weight. Okay, it should be like less weight, then strength should be like more. Okay, strength should be like high. Okay, so here, if I'm going to have for a less weight than strength is high, we are going to have a material combination. Okay, where the cost of that material combination is going to be like high. If we are having any defect product here, then the entire is going to be like a loss. And also, if you are not detecting the defect on this, if as it's going to be for an aircraft, if anything happens on the what is that defect, then it's going to create a serious impact on the aircraft. Okay, so in Wipro 3D, okay, you can directly go to the website Wipro 3D. Where they are having a real-time problems. Okay, then everyone knows about Tata Steels. Okay, Tata Steel. Okay, so there they are manufacturing the again product. Okay, product using what is that layered approach. Okay, for aircraft. Okay, for aircraft only again. So they are also having a serious set of problems to be solved. Okay, so we are also okay. Our team also has contacted the Tata Steels for getting a funded project. Okay, it's still on open call only. Anybody in the participant list can go to the website and take their problem. Okay, their work is to detect the defect before it is there is a product is developed. So that is what. Then TVS. Okay, we all know TVS. Okay, it's from Tamilnadu. Okay, so there also they are manufacturing a number of products. Mostly TVS is assembling, but they are manufacturing few things. Okay, so there also they need this defect detection. So these are all the three. Okay, that is leading place in a company where they required the solution from the institution side. Okay, particularly from the students. Okay, they are encouraging on internships and everything. You can contact them directly, okay, through the website. Sir, I've done with my side, sir. Thank you for the opportunity given. Okay, so it's a 1 hour presentation. If it's going to be like a 1 day complete presentation, we can go from that is basic to the advanced level. Okay, thanks for the opportunity, sir.
Thank you, sir. In case any queries, we will post your mail ID so that they can directly contact you.
Yes, sir. It's welcome. Okay.
Right.
I'm
So
ready to call.
Yeah, on behalf
Even
of
if people are having any while taking the code from the Kaggle, what we have given, if you are finding difficulty in understanding that code, then you can mail us. Okay, there is 2 students and 2 professors will be there. You can mail to anyone.
So thank you, sir. On behalf of Swarnandhra College of Engineering Technology and Department of Mechanical Engineering, I would like to extend my heartfelt gratitude to our today's speaker, Dr. Gopinath, who shared his expertise in our knowledge sharing forum. This session will be an eye-opening for egg budding researchers, especially in the field of AI, ML, and computer-based interdisciplinary. Sir, your presentation has been incredibly informative and thought-provoking, and you have shedded a light to overall on the experiences. And thanks for your expertise. Thank you once
sir.
again.
Thank you, sir. Thank you. Shall I
So, yes,
close the
sir.
meeting, sir?
Yes, sir.
Okay. Thank you.
Thank you. So, dear participants, we have the second session. After 2 minutes.
Sure, sir.
Good evening, ma'am.
Good evening, sir.
Welcome, ma'am. Ma'am, shall we start, ma'am?
Yeah, yes, sir. Yes, sure.
So, dear participants, we are now in the second session by Dr. Aarthy, Professor, Department of Computer Science, VIT, Vellore. So, on behalf of Swarnandhra College of Engineering Technology, Department of Mechanical Engineering, I welcome our today's session second speaker, Dr. Aarthy. So before getting into our session, let me give a brief introduction about today's speaker. Madam has completed his post-graduation technology during the year 2011-18 under the topic A Framework to Recognize and Detect Breast Cancer from Mammogram and Digital Infrared Thermal Image. Madam has a vast experience in the professional as well as the various administrative experiences and hold various positions as an administrative. In addition, Madam is also Assistant Director for Student Welfare in VIT. So, Madam has got a funding in 2019 under the topic An Efficient Multi-Angle Weight Updated Harlick and Relevance Vector Machine Algorithm for Classifying Diabetic Food from Medical Thermal Imaging. Madam also got some awards and recognitions towards the contribution to research during the year 2015, 16, 19, 20, and 21. Madam is also in various journals, reviewer as well as in the editorial board, reviewer in IGI Global, reviewer in InterScience, and reviewer in INASS. Madam is also having various scientific and professional society memberships. And yes, Madam also presented, delivered lectures in various institutions. So with this few brief introduction, I would like to give over the session to Madam. Madam, welcome, ma'am.
Thank you for your warm welcome, sir. I'm not taking much of your time. I'm directly moving on to the presentation. Hope my slide is visible for you all.
Yes, ma'am.
Yeah, okay. So before getting into the implementation and hands-on part, right, let me give you an overview why more particular about defect detections and through machine learning algorithms, right? So I hope all of you might be working on the various machine learning, right? So you may be coming across the defect in the the chip, or you may be finding the defect when you optimize the design. There might be a failure prediction, or it can also be used in detecting the tumors, right? So what we normally do it in with respect to the mechanical engineering is design optimization. How we can optimize it, how we can minimize the weight, all those parts will be done by the machine learning. So this will help you to enhance and give you a better performance in designing a machines, and how far it will be affected in the failure predictions, how a material can be calibrated, and how it can reduce the testing and the calibration time in making certain materials. So obviously, without the mechanical missions, right, we will not be able to live in this environment. So even our 3D missions where you have the MRI and you have ultrasound images where the mission play a major role in detecting the various diseases we have across the world, right? We can use that missions, how the mission will be able to sustain and detect the tumors can also be used in this mechanical part, how the transformation of your mechanical engineering in the ways of AI and ML, right? So why machine learning? So what is that a machine learning is all about is, so giving a set of informations, right? So you have a lot of informations and you need to process those informations. So you wanted to train the machine so that the human error or the human work will be reduced. So there are various steps how we can train the machinist by collecting the proper data, right? So say for example, there is a paramedical industries. So when you look at the paramedical industry, the drug mapping of the drugs, right? When you look at the paracetamol tablet of 10, might be one might be unsealed, the cap might be unsealed, right? So what data we feed, how the data to be is the first step, the first and foremost step in machine learning. Making your mission to learn the environment is what you wanted to do the first step. That is what you call it as a collecting of data, right? So when you're working on the defects in a paramedical design, right? A drug of 10 by 10, right? There might be a cutting might be in a different position. The cap might not be in a properly closed or sealed one, right? So what you feed is what you get it at the end, right? So when you collect the data, you have to instruct the machine properly. So all these machines are built up with an artificial neurons. So when you are a human being, it is the human being's responsibility to train the system, right? So when we were a kid, right, we have been in the training process, right? The once the kid is born, right, we're not sure that the kid will not wake up or immediately start walking it. So we train the kid. So how we train it is, we say that this is a routine, we do it, right? Some kids might eat in the left hand, but we say that we have to eat it in the right hand because we have been trained in that way that we are supposed to eat in the right hand, right? So this training, how you feed your data, likewise only the kids gets trained, right? So basically the machines also gets trained based on what you feed into the system. So if you feed an irrelevant data, right, the system output will also be an irrelevant. So the most important part of machine learning is how relevant data you collected. So once you collect the data, you need to prepare those data. So when I say a preparation of data, right, it comes with a two part. One, you call it as a training. So where you say that this is the image and this is how it should be, right? So that you call it as a train. It is say that all the working how it should be is being given in the training, and all the individual images what you go right and check with the training data set and say that it has been mapped like this. Because of this is defect. Because of the cap is not sealed properly, so this comes under the defect product. So all the each individual image you process through that machine will be considered as a testing data, right? So we normally train the model by using the trained data where you have the defect images and also an non-defect images, right? So only those images will be trained. All the testing data you use it will not be a trained model. It will be a raw input. So what is that you do it? So in the previous session, you might have come across with a lot of machine learning algorithm like supervised, unsupervised, recursive, ensemble model, right? So these are all the various machine learning, how you can choose your model, right? These model choosing depends upon the data you have, right? So if your data is going to be a completely a numerical data, you don't have any image. It's all about say if I have a body mass index and based upon my body mass index, I can say that I'm obese or I'm on a normal weight, right? So keeping those important factors and these data become a categorical data. It is all an input data. So when it is all these are input or a numerical data, then we go up with the supervised learning. So when your data is more not with any target, so you say that you are obese or not obese without anything. If you have only the raw set of data, then you call those data to be a non-categorical data or uncategorical data, where you go with the clustering. You group all the similar data together and make it as one different model. So what model to choose depends upon the expertise, how you choose your data, right? So am I clear till this? Yes. Okay. So once this is done, right? So once a model is being trained, you need to train. Hello. Am I audible, sir?
Yes, ma'am. Yes, ma'am. Audible.
Yeah, yes, fine. Okay. So I'll just go on with a sample example how a defect can be detected, right? So we'll go with the leather defect.
Ma'am, your screen is not visible, ma'am. Ma'am. Ma'am, your voice is also not audible. Your screen is also not visible.
Sorry for the inconvenience. Yes. Is my screen is visible?
Yes, ma'am. Yes.
Yeah, yes. Sorry for the inconvenience here. Here I have just shown you the leather defect deduction. So here we have a pinhole leather images. So this images as a pin kind of holes in the all the images, right? So this is one kind of leather defect, and this is the non-defective images. It doesn't have any defects in it. And we also have another defects like loose grains, growth mark, and grain off, and then the leather folding marks, right? So with this leather defect deduction only, we are going to see an hands-on problem, how to work on a orange tool, right? So orange is an tool. You can use that orange tool to you can do your machine learning algorithms using this tool, right? So it works both on data and also on the images, right? So now it is all an orange tool. If you search on a Google with orange, you can find out the link and you can just download this and you can use the GUI given in this particular app to download. You can use directly the input and you can work on the various machine learning algorithm at the initial stage. Since you may not be familiar with coding part, so I thought that this particular tool will help you in doing an interdisciplinary research perspectives. So that's the reason we have just showing you the orange tool here. So first, I'm just going to import my images. So I'll just directly click on import images in image analytics. And then I'll double click on that. So I'll just go browse it and I'll be finding the folder. So I'll select the complete folder. There are around 3,600 images of 6 categories. So I have already shown you the categories like pinhole, non-defective, loose grain, growth mark, grain off, and folding marks. These are all the defects, right? There are only one folder with a non-defective. So 5 folders with a defective one and 1 with a non-defective one. So once that is being processed, this image need to be converted to a data. So that will be done by a image embedded, right? What we do is the image here given us will be converted into a data here. So when you look at and you click on this, you will be able to see how a data is being getting converted, right? So there are different embedded algorithms we are using here to convert. So we'll just look for VGG16. I'll tell you what that model is all about, right? So once your image is embedded, you need to convert it into a data table, right? So you will have the embed and then you will go for a data table. So where you will read the image. Once you read, you process the image in the image embedding, and then the processed data will be available in the data table. So once it is done, you can apply the various machine learning algorithm like supervised and non-supervised algorithm based on the data you have. Here, I'm just taking it as a neural network. Your neural network is nothing but how your machine, right, is able to work. Here, I have just taken the neurons, right? All the data will be converted into a neurons, and between you have an hidden layers, hidden neurons, and how those neurons will work. So after this neural network, you need to apply and see how it works. What is the final output here, right? So you just do it with the final output. The same way from the data table also, you need to pass on to the test and score. And then you look at that with the graph and then a matrix, right? So the embedding is taking a long time. So there are different embedding algorithms. You can go with any of the embedding algorithms. So your inception V3 is quite faster, right? So that's the reason I've just chosen with embedding algorithms. So once the images has been embedded, right, you can visualize those images in terms of data, right? So are you able to visualize it as a data? So all the images are of size 227 by 227. So all the images with the different categories, it will be available here. So there are around 2048 features will be selected and it will be given here. Okay. So once it is given, so you will be developing a neurons here. So what this neuron do is it will give multiple instructions to your data. All the possibility in finding a defect will be passed on to this hidden neurons. Say for example, first I may see that the defect is a pinhole. They may also have a foldable defect. So all those defects will be detected and it will be given in the hidden layers. So it is nothing but training your brain to do certain activities, right? So the model is getting trained here. In the meantime, if you have any doubts, you can ask until the model gets trained. Yes, any doubts? So all these model require a little bit of high-end system because of its because the data is being trained a lot. So because of that reason, it requires an high-end system. So only then it will be able to perform better. So we'll work on. So here we'll be creating a model here. So I'm just passing the data and I'll just repeat the step because of its time. I'm just stopping. I'm just going with the data here. Okay. Now I'll just show you how our data is being loaded here. And then I'll show you for the image. Okay. So here I'm just loading a data set which is already available. Here it is the leaf data set here, which is already available. And here the iris is a categorical data, which means that I'm saying that that is a target class. The others I name it as a features, right? So, and then I apply it. So once I do apply it from here, I'm just giving it to a data sample. So where the data will be divided into a training and testing data. I can apply the various machine learning algorithms. So here we'll apply decision tree. Right? We can also apply a vector mission. So we apply different algorithms on it. And you can also apply a neural network, the neurons to train the data. Right. Once this is done, and you can also pass the data from here to the test and score. Someone have raised a hand. If you have doubts, please, shall we?
Ma'am, good evening. I'm Srinivasan.
Yeah. Yes.
So, ma'am,
Yes,
if
sir.
there is a data set, how can you separate this as a training set and another one is testing set?
Yes, sir. Yes. I'm coming to that. So I'm just going with a Python thing, and I'll come back to you how to differentiate into a trained and a testing. So every time, right? So suppose if you have 100 rows of data, always the 66% of data from that will be considered as a trained data, and the remaining 33 or 34% will be considered as a test data. That's a normal standardized rule we have for the machine learning algorithm, keeping around the 66 or 67% for trained data. From the overall data, you will keep 67% as your trained, and 33% or 34% is for the testing data set.
But which
That's a
66?
standard rule. That's a standard rule. It has been followed.
No, ma'am. We are having some set of data, but how can we identify this 66%? Which 66?
So you will. I'll show you. Will randomly the system will take it up. When I point it here in this tool, right? Here the data sampler is given, right? So it will take. So I have given a fixed proportion of data as 70%, right? So which means that the 70% of the data will be a trained data, and the remaining 30% of my data, the file which I give, will be the testing data. Okay, I can also fix a sample. So I can also have first 100 samples as my trained data, right? It all depends on the data you give here. Are you able to see it? Sir?
Yes, ma'am.
Yeah. So here you can fix it either as a 66% or actual norms is 66 and 30, 67 and 33%. The 67% is fixed for your training data. So that's the training data we pass on, right? Here in this tool, the data will be fed in the file, and from that only the 67% will be going as a training data set here. I can also fix a sample size. So the overall data size is 150 instances. Out of that 150 instances, I can keep the first 100 instances as my sample data, or I can fix that as my training data set, right? Or I can change it to 80% also. 80, the first 80 instances or a random 80 instances will be taken up as a trained data set, and the remaining out of 150, if 80 goes, the remaining 70 will be taken up for the testing data. Yes, sir?
Okay.
Yeah. So this choice
that
is
taken
left to the...
randomly by the... Yeah, it is taken randomly by the algorithm itself.
Yeah. Here it is a built-in GUI, sir. The orange tool is a built-in GUI. So you need not write the algorithm, right? So the algorithm is already written and it has a built-in GUI. So as an initial state for a mechanical to write a code, right? So I'm just showing it as a tool, right? So I'll just go ahead and show you in terms of code also, right? So here the built-in tool, the data sampler, does the job of splitting your data into a training and testing. So when you click on it, and you can give it as a fixed proportion of data 67%, or you can fix the sample size to 80 or 90 instances, or you can divide it into number of other subset, and you can use that as a sample data set also, right? So here, once a sample test is given, that need to be, the algorithm will be incorporated. So sir might have been said about your decision tree, right? So here the decision tree is a binary tree, which is having a number of instances in leaves. Since it is a binary tree, it can have only two leaves at the bottom. So every root node will have only two trees, one on the left and the other one on the right. So how far the depth of the tree it can be maximized to a level of 100 here, right? So all these can also be written as a code also, right? So the code part I'll show you in the later part of my slide. So initially, just wanted to give you a brief how these machine learning algorithms supports and help you using a tools, right? So there are three different algorithms I have used. One is your decision tree, the other one is SVM, the other one is a neural network. So all these three algorithms are a built-in algorithm. So whatever the coding does, it has been already done and it is available as a user-friendly tool. So it is just a drag and drop for us to place the algorithm. So it is all built in there. So once you have learned and you have a test score, you can have a test score and you can have a curve. So how these data are being analyzed, right? So this, you call it as your evaluation result, the confusion matrix, and the ROC analysis is called as your evaluation metric. So here, when you look at these metric, right? So I can directly say that these are the three different, features I have for this particular data. But actually it is of 40, but all 40 has been deducted correctly. And none of them has been deducted as a false data here. So when you look at the iris versicolor, right, the predicted one out of 33 images, no, it has predicted only 30 correctly and the 3 has been predicted wrong, which means that there is a defect in that particular image. So that image has been misclassified as another medicine also, right? When you check for all paracetamol medicine, but looking at this science size, it will be classified as Dolo 650 also, right? So based on the color or other different features, the size and everything matters here. So here, when you look at it, versicolor actually has 33 versicolors, but 3 of those images have been misclassified as virginica. So which is just flowers classification. And when you look at the virginica, actually it is to be classified correctly with 30 and 2 has been misclassified. When you look at the SVM algorithm, it has correctly classified perfectly the sedosa image, whereas the other 2 images have been misclassified. So the same thing applies for a tree and your neural network algorithms. So when you look at the neural network algorithm, it has classified only 28 correctly and there are misclassified as 5. Why there is a difference in all the algorithm is what kind of features and what are the hidden layers have been there considered is a difference, right? So when you look at your SVM algorithm, it has classified that particular sedosa images alone correctly, which means that the training is properly done so that all possible ways have been correctly trained and it has been correctly classified. When you look at the versicolor, which means that we are lagging with some of the defect which need to be identified still more clear to make that to be correctly identified that without a non-defective one, right? So these are the various algorithms and this gives you an ROC curve. When you look at the ROC curve, right, it should always be in the line of 1. The region of curve should always reach the point of 1. So only then you say that the particular algorithm is a better algorithm. It best suits your data. So when it is not a line of curve is not of reaching the 1 point, right, which means that the data and the algorithm you have choose as lot of misclassification for this particular data. This particular algorithm doesn't suit. That's what the conclusion is, right? So hope I have conveyed what it is, right? So I'll just go in detail about your defect deductions, right? So here is an algorithm. Someone might have been asking about how will I classify my data into a trained one and a test one, right? Am I clear? Am I audible and am I clear?
Yes, madam.
Yes.
Yes, madam.
Yeah, yes. So your Kaggle is an environment where you can work on a large number of data sets. So when I showed you a leather defect deduction data, it consists of around 3,600 images. When you try to run it on a normal CPU, right, the CPU will not support your system, right? It will not be able to look into the working how the system works to classify or train all those 3600 images in different aspects, right? It will be very difficult. So the Kaggle is an environment where you will be working on the GPU, right? Where you have a graphical user interface system, where, so that it will be a better and a faster rate in classifying your data, right? So your NumPy as NP and Pandas as PD I have given is, I'm just importing the data. So what is NumPy is a numerical Python. So numerical, all my numerical data will be considered as NumPy. Those are all my numerical Python. So if I wanted to work on arrays, so I have to use a Pandas. To process all my data, I need to use a Pandas. So data in the sense, it is in the number of rows and columns. If I have a rows and columns, then you name it as a data processing, or you call it as a reading the CSV file. So all those data reading process and processing those data will be done by the Pandas file here. These are all built in the library inside a Python, right? So import NumPy as NP. So I am just naming that NumPy as NP. Henceforth, wherever I wanted to use a numerical Python, I'll be referring only as NP here, right? So once that is done, I have to load the data. So for that loading the data, when you look at this corner, right, I have an option called add data here, right? So you will click on add data and it will find the data which are available, right? So the first thing is here we are going to look on leather defect deduction. These data is already loaded in my particular thing. So if you wanted to load the data, you just click on the plus sign. Since the data is already loaded, okay. Since the data is already loaded here, I am able to get it as a remove data set. So I need not remove it. If you can just click on the plus sign, it will add that particular data set into the image, right? Into the our particular code. Now I'm just showing an example as thermal. I'm just adding those data set into it. So I'll get it as input. In that already I have loaded the leather defect detection. At the bottom, I have also loaded the thermal. I wanted to remove this particular data set from it. I can remove it from more action. I can click, right click, and then I can remove that particular data, right? So once I have read, I have just, so inside a Kaggle is what the default environment. Inside that, I have given it as input. This location is a default location. So where you load your input data. So once you load the input data, if you try running it, it will start reading all the data from the particular location. Yes, can you all see that particular locations? So it will start reading all the 3600 images, so on various categories. Right. So once I read the data, so what I do is I need to make that particular data as my test and train the data set. I wanted to divide it into a training and testing data set. So all my trained DIR, the directory for trained data set is inside Kaggle input. So what is the file name I have? Leather defect deduction. The same I have used here, leather defect deduction. Followed by that, I have a folder called leather defect classification. However, I have in this corner, the same version I'll be using it for training and testing data set. Right? Here, I have used another test data set here. So the trained data set is the leather defect, and for testing, I have used some other random location. I have taken the test images. So once it is done, so I'll just print the directory. So it will all taking that particular training and testing directory will be loaded with those images. Once I have loaded with the images, what I have to do is I have to split the data into training and testing. So here I have taken the trained DIR and I have used a validation split of 0.2, which means that 20% of the data I have taken it for testing. The remaining whatever data I have in the training is what I have used for training the data set. So out of 100%, out of 3,600 data, I have used 2,880 data for training, and the remaining, that is the 20% of the entire 3,600 data will be used for testing it. Here I have named it as a validation split. Yes, so I'll run this. So once I run, sorry, I didn't run the previous questions. So here, when I run it, the validation split is equal to 0.2. So if I want, I can also change it to 0.3, which means that the 30% of the data will be considered as my testing. Can you see if the training data is reduced to 70%? That is 2520 is only being considered for the training, and the remaining is being considered as a testing data here. Right? So I can validate my data. Once I have done the validation, I have given out of this 3,600, what is my validated data? So if you want, let it be as 30%. So when I use 30%, it will give me around 1,080 is for testing, and 2,520 I have used it for training it. When I add this training and testing, I'll be getting around 3,600 as my original data, right? So once I have found that data, so I need to print the label of those data. So the label is nothing but my folder name. These all, you call it as a labels here. So I need to get each and every element of my table. So once I get the each element, I name each of the class name, which means that out of this, these are all my class group. One is with a defect pinhole, one with a folder with a non-defective, which means that it is correctly classified. It is a pakka leather non-defective data. Loose grain is a defective data. Growth mark is a defective data. Grain off is my defect data, and folding mark is my defect data. So I have named my class. So once I have named my class, I have just shown you a sample of all the images here, right? So these are the subplot. I'm just plotting the images on the various defects. I have just taken the first 9 images. So for I in range of 9, right? First 9 images, I have taken it up and I have just plotted the subplot 3 by 3 matrix. That is what I have given in the subplot. It is a 3 by 3 matrix. So it has been running, the number of column will be run for I plus 1, right? And then I'm just printing the data here. So I'm just showing you how a data will look here. So it's just a visualization of my data. So once the visualization of my data is done, I have to group it up into a batch of images and batch of labels. What is label is nothing but the folding mark, grain off. These are the labels. And when it is for the other cases, it is the image. So inside that, what are all the images I have? So once I do it, I need to rescale it into a data now, right? Whatever I have it of multiple colors, now I need to rescale it into a black and white or grayscale images. So I just use a normalization and make it as a grayscale image. So grayscale images, why we are concentrating on grayscale images? Only then the pixel value will be ranging only from 0 to 1. So all the variations of your data will be between 0 to 1 only. So that's the reason we are using a data in a normalized data. So here the data has been normalized with a minimum value as this one and a maximum value as this one. So once the data has been normalized, I'll be giving it to a layer, right? So what is VGG16? So your VGG16 is a model. So I have an input model and then I am giving it to a convolution network, right? So I'll just show you your VGG model. So I've used multiple models, so I'll just share the code also for you. So here is a VGG model here. So I'll explain you with the table here in this side. Right? Is my both the screen is visible?
Yes, madam.
Is my
Visible,
both
madam.
the screen? Yes, yeah, yes. So here I have given an input image. I have also given an input here, right? With a size as 227, 227 and with a single dimension data. One stands for a single dimension. It is a 1D, 2D data. It is not a 3-dimensional data. So once that is done, I need to name the number of classes. So how many classes I have? I have a class label of 6. 5 as a defective class and 1 as a non-defective class. So the number of classes, I'll define it here as 6. So now the next part is your creating a pre-trained model. So this model is creating this particular convolution network and then again a convolution network and then a match pooling network and repeating this for twice. So how it will be is first an input, then the next layer will be convolution layer and again a convolution layer followed by a match pooling layer. Again, a convolution because it is repeating it for twice. Similarly, there is also another 3 different layer which repeats for thrice. So why is it required? Why you require a convolution layer is how far you create an hidden layer and make your data to be verified and trained in all the aspects. So because of that reason only you have multiple layers here. So here the VGG16 model is being built and here you're giving the weight as ImageNet and the input shape is this one. So once it is done, I'm just creating a model is equal to sequential. I'm just adding the convolution layer here and I'm just start adding all my model dot layer, right? So once all the layer is added, you will exactly see this particular model itself in the PPT also, right? So here you have the same model. So the input model, then 2 block convolution and 1 match pooling, and again 1, 2 block match pooling, and again 3 convolution with match pooling, and that process will be repeated thrice. 1, 2, 3, 3 convolution and 1 match pooling. And again 3 convolution with match pooling. After that, you are on flattened layer, 2 dense layer, and the same diagram is what being repeated in this particular VGG16. So these are all a pre-trained model which is readily available and it can be used for directly for the initial user. So all these model can also be added with a different layer also. I can also create my own model by just adding model add. I can create a dense here, right? I can create a dense here with the same 4096 and with an activation as my ReLU. So these are all the different algorithms which is available, right? By adding a layer or adding a convolution model, right? I can create my own model. By then you can say that my particular work becomes a more specific model, which has not been repeated by other researchers here. So you can create your own model and you can show your novelty that how far these model will be helping your data, right? Once the model is being built, you need to check or fit that particular model into our data, right? You have to train that particular model and you have to check for the fitness. So here the model is being checked for the fitness here. So once the model is being fit, right? I'm just running it for 2 epochs. When I run it for 10 times, right? Each time it will run for 45 minutes, 45 times. Each and every data will be running for 45 times and into 2, which means that it will run for 90 times. So since due to the time constraint, I'm just running and showing it for epoch of 2. Right? Any doubts? So once the model is done, so it will start executing it here, right? Which means that for the first set of model is built. So for the first epoch, it will run for 40 times. So that with a accuracy time of 14.22 with a loss accuracy as just 12%. When your data gets trained and trained more, the accuracy will also keep on increasing. So when you look at for the second time, right, the accuracy have increased slightly with 15%. Okay. So the process will take some time. So we'll wait and just see. In the meantime, if you have any doubts, you can ask.
Good evening, ma'am.
Yeah, yes, sir.
When you are finding about the model, so for example, if in case if you are taking about a regression or else SVM algorithm, how we can able to differ with the model? Everyone we have been using the algorithm, same algorithm. By varying the testing and the train data, we are differing the model.
Is it not based on the differing the model based on the testing or training, sir? It is by the parameter you change it, right? So when you look at the vector, right, support vector, right? So you may be creating multiple vectors based on the kernel, whether it is a linear or a non-linear data. You create a vector and you try to fit in based on the your number of vectors you create. Right? Suppose it defects. So for this particular data or for my particular data, it is enough if I use a vector of only two support vectors. Then for my data, I'll be using a vector of 2 and I'll be defining with a better accuracy. So it is just again will be on the how far the data is being learned by your machine.
Okay, ma'am. Thank you, ma'am.
So it is all depends upon, see, when I take a defect detection, what I showed is the neurons have been failed, right? So in classifying the data, but when I look at the SVM, the vectors, right? How many vectors I created on that algorithm, add a better result, right? So when you look at this, right? So I have used an SVM. So the SVM has a regression value and it is going to be a linear kernel. So when I use a linear data, I'll just show you how my data accuracy is. So I have given an accuracy of 99.6, right? So if I change that SVM algorithm into a polynomial, or a sigmoid graph, the kernel functionality will define how my data is being trained on that. So when you look at this, when you look at it for the sigmoidal graph, the test score, when you look at it, is only 96% of accuracy, right? So when the same algorithm, when you look at it for a linear kernel, X and Y, MX plus C is your linear kernel, right? So for that, you look at the accuracy, it has given you around 99.6. Right. So it all how far that particular vectors is supporting your data. So if I give you a choice and I have run a multiple algorithm, one SVM with a linear mapping as its line, right? Linear is nothing but an mx plus c, and another one with a sigmoid function, right, which goes on a peak and then comes down, right? I have a two different algorithm, two different support vectors over there. I divide the data linearly here, another one with a non-linear thing on a sigmoid data. I just segregate data. So how far I divide those data matters when I take it up for my data set. Here, for this particular iris data set, the linear separation is what is more accurate than going with a sigmoid where I have a 3 support vectors, right? One on the right, another one on the left, another one on the peak. That's your sigmoid, right? So a sigmoid graph goes in this. So when you look at your sigmoid graph, so it will be like this, right? So you have a negative end, a positive end, and a peak for a sigmoid. When it is come for the sigmoid, I have a support vector here as S1. The peak will have a support vector as S2, and another positive side will be my support vector 3. When I divide the data linearly, it is only my MH plus C, where I can have only one of my support vector. It will be on this particular line alone, right? So here, when I take up data here in this iris, my linear SVM is better than my non-linear SVM. That doesn't suit for all the data set I have in my data. So when I look at that for the best cancer data set, I'll be having a the sigmoid one will have a better result than a linear data set. So how far the algorithm is better fitting it for your data is what you have to look at. So in order to have a better result. Yes. So now if you look at for the first epoch itself, when I've done with my 20 run, I'm keep on training my data. So for the first 20 training data itself, my accuracy have come for 30. When it goes after completing my first epoch itself, it will reach around 70 or 80. When I run it for multiple times of 100 or 200 times, I'll be having a better result. So here it is on how far the data is getting trained. When I train more and more, there is a lot of chance that my data will have an 100% accuracy also. And there is a lot of other chance also. The data may also lose its vulnerability and it goes in another way, which may also result in lesser accuracy also. It means that how far your algorithm, the algorithm choosing and the data set is being fitting here. That's what the feasibility study you have to take it up before going up and doing with the model.
Ma'am.
Yes.
Ma'am, based on this accuracy level itself, can we decide the model is good or bad? Because sometimes it may stick with the local optima or local better solutions than the global.
So the accuracy is one of the major parameter. With that parameter itself, you can declare that the particular algorithm and the data set is much suitable, and you can go ahead and say that this particular algorithm gives a better result, and you can give a comparative study on that. So the accuracy is one of the major parameters to say that the particular algorithm works fine.
Ma'am, one more question.
Yes, sir.
Ma'am, in practical situation, actually, we are collecting data. We are having some n number of data, 100 number of data. But is it from that we are getting some results? But can it be applied globally? For example, if it is taken for a medical purpose, then we are finding out some results. Then can we apply it globally? That is not possible. No, that is we need a larger number of data to do it.
When you wanted to have it on a globally, right? So there are a lot of data should be involved. Right? So what we do is only around 1 or 2% of data where we say that this model, if it is work on this particular set of data, it will work better and it will give you a better result. So the experimental part lies at that point when we try to directly run it on with a larger number of data. With a few trained data, around some 80% of the trained data, we say that this particular model will look better or works better for these kind of data set, right? But again, when you look at a different data set and this 80% of the data set you've already taken and trained it may not suit another data set. At that point, you may have a less accuracy. What you do is you take that data also as your trained data and you start training your system more. So that's what we normally do it in our the drug medicine package, how you do it, the correction in your medicinal package. So nowadays you have the drug defect, the medicinal drug package defect has been easily identified by a machine learning algorithm only. So if a packet is not filled by a tablet, right? So those are all the defects which can be easily identified, right? So those images have been loaded already. So if all the 10 in the packet, if all 10 have been loaded, that will be the given in the data. So, and it will pass the test. Otherwise, that says that the packing is not good and it will go for a repacking. Right? So that's what we normally do it in a drug pharmaceutical company. And the same thing is applicable in your, where we come up with the, we have it in the airport, right? So the airport screening is not, doesn't open all the data. We just keep the, our luggage. So, but they screen the entire images inside that, right? So how the light gets penetrated and how it's been captured is because of that edge detection. So each and every object inside the luggage is being considered as an object and it will start marking the points and it will try to frame the points, right? So the once it frames, if it looks like a bottle, it try to refigure it and make it as a bottle, right? If it looks as like a wallet, which the way the data is already loaded, right, there it will take it up as a wallet. So that's what the edges have been marked and you'll be able to see the edges alone over there in the scanning. Right. So how the data can be utilized is what we have to think and we have to work on it. So when I try to run it for the first epoch for 40, the accuracy level is very less, which comes only with the 46%. So in sometimes the algorithm in the first epoch itself, it will give you around more than 50%. But now it is start increasing. We started with 0.12 initially. Now it has come to around 50%. So it will now start with my second epoch. Right? I cannot show you much of deviations in 2 epochs. When the same data set is run on 10 or 15 epochs, you may see a better, good result. Right? The accuracy is very less here. Because the data is not get trained properly here. Due to the time constraint, I have just shown you only the 2 epochs, which means that I'm running the entire data set only twice for the training purpose. So when I train more, I'll be able to get a better result. Not taking much of your time. Just wait for another 5 more minutes to complete this epoch. Right? Sorry for the delay. Any other doubts? Okay, once the model is getting trained, right? So once it is trained, I'll start validating it, right? So this is for the validation part. So I'll start giving a loss. What is the data I have lost on the training and what is the data I have lost on my training data set? So, and then I'll be plotting it. So the validation loss should be very minimal and the training loss should also be very minimal. So the minimal, the training loss and the validation loss, the better the accuracy you will have. Right? Thank you. Thank you, sir.
Thank you, ma'am. Dear participants, if you have any queries, you can post your queries.
So since it was 1 hour of time, right? So I couldn't start and say you from the base of your Python. My few might be familiar with Python and most of them might not be familiar with Python. So sorry for that inconvenience, right? Hope I have just inculcated what machine learning is and I have given you a better hands-on session, I guess.
So I hope it was an informative session. Thank you, ma'am. If there is any queries, I will post your mail ID so that they can directly contact you and clarify their doubts. So on behalf of Swarnandhra College of Engineering and Technology, we would like to extend my heartfelt gratitude to our today's speaker, Dr. Aarthy, Professor, Department of Information Security, Vellore Institute of Technology, Vellore, Tamilnadu, who has shared her expertise in this knowledge sharing platform. Madam, your presentation has been incredibly informative, and we are all grateful for the knowledge and the inspiration you shared through this hands-on session. And also, thank you so much, Madam, for having accepted our invitation on behalf of Organizing Committee and Department of Mechanical Engineering, having accepted our invitation with short notice. And we hope that we have opportunity in future also to work with you again in future programs. Thank you so much, ma'am.
Pleasure is mine, sir. Thanks a lot. And thank you all for being such a wonderful colleagues here to give me a nice platform to explain my knowledge to you all. So looking forward to work with all. Thank you.
Thank you, ma'am.
Thank you, sir. Shall we leave, sir? Shall I leave? Yeah. Thank you, sir.
Welcome. Thank you. Dear participants, thank you for your active participation for today's session in both session 1 and 2, and actively engaging yourself in clarifying the doubts and interacting with the session speakers. And the feedback and attendance links are posted in the chat box of Zoom as well as in the YouTube live session. So you can fill this attendance and feedback form. It will be active for another 15 minutes. And for tomorrow's session, we have session 1 by Dr. Sunil Ratnakumar under the topic Composite Materials Using Powder Metallurgy Technique. And session 2 by Dr. K. Kamalakanan, Professor from SRM University under the topic Control Strategies of Magneto-Rheological Dampers in Automotive Applications. So these are the 2 sessions tomorrow. And I thank each and every one of you for your active engagement in this FDP and active participation and happy learning. Thank you all. Please complete your attendance and feedback form. It will be active for next 10 minutes. Thank you. Dear participants, so the attendance and feedback form will be active only for the next 5 minutes. And thank you for your active participation. Happy learning. We'll see tomorrow. Thank you.